go over the last little bit of the homework explicitly because it was kind of tricky. The last little bit of the homework was to change the print function in the other file, in the runner file. Does anybody want to explain how they managed to do that? Any volunteers?
You import built-ins, and then built-ins have a function called built-ins.print. You just set it to an instance of your print class.
Yep. So there's different ways to do it, but the way that I did it was, it turns out in Python there's this module import built-ins. Built-ins? Built-ins is a module that contains all the built-in functions like print, sum, min, max. You can import that, and it turns out when you use a built-in function, Python checks for the global scope first, and then it checks in this module. So if it can't find a print defined anywhere in your file, it's going to look here next. So the way that I overrode the print function was, I had my class here, and you can write whatever you want in this class basically. But then at the end, you just say built-ins dot print equals printer 2. And that does the trick. Setting that correctly.
Is that within the class or outside?
No, this is outside of the class. So you've got your class definition here, but then after the class definition, just in the file tree, you can do that. So that's how I did it. And what this does is because Python checks for the built-ins module for anything built in, if you change what the built-ins module says print is, then you've changed what print is. And that'll happen in all files, everywhere in the Python interpreter. It's not just where you get imported. Did anybody run into any issues trying to do this?
You do have to make the print inside the class.
Yeah.
You make sure that it's the old print and not.
Yeah, so the problem is because print gets looked up in this module here, if you change what print is to this, if you used print inside of your printer class, then all of a sudden you have an infinite loop going on because you're calling print and then it's looking up print and it's an instance, and your instance calls print and it's an instance, and it looks up print and it's an instance. And so I think you get a recursion error. Yeah. So that was the subtle other thing is in order to do this, you should probably save the built-in print. So I did something like this, underscore equals built-ins dot print. And so you save the original built-in print, you use the original built-in print here, and then you override the built-in print, but you still have the saved copy here. So there are a couple of things that you had to do in order to get this to work, and this is all possible because functions are objects. This would not be possible if functions were some special type. No, functions are just attributes in a module, and you can change those attributes just like you can change any variable. So functions are objects, cool stuff. In case you're curious, this trick here of changing the code in a module that isn't yours is called monkey patching. And it's really easy to do in Python. It turns out that in Python, if you wanted to, you could say this. You could import math, and then just say math.py equals 5. And then everywhere, pi will be 5. That's technically monkey patching. You're changing this supposedly constant in some other library that you probably should not be changing. The cool thing is that it doesn't just work for constants, it works for functions, it works for classes, it works for whatever you want. So there's some cool pip installs that will monkey patch backport newer versions of Python to older versions of Python. So if you want to use like a function that was introduced in Python 3.9, but you're in Python 3.5, sometimes you can find a pip install that will monkey patch that back for you, which is pretty cool. Questions about this?
I was also like reading up about it, and like one example that they were giving is like if you're like making a reference to a database, but you don't want to necessarily have that hook up every time while you're testing.
Yeah.
Or you could monkey patch in like just like a constant data set.
Yeah, great point. Probably the most legitimate. So monkey patching is generally discouraged because, for one thing, it has unexpected behavior. Like doing that, who knows what that's going to do? That's pretty wild. So first of all, it's dangerous, and second of all, it's not compatible with other codes that's trying to monkey patch. Like, let's say we're writing this library and we depend on pi being 5, but then we import another library and it depends on pi being 2. Then whichever monkey patch happens last is going to take precedence, and so it's generally discouraged to do this kind of thing. But the most legitimate use case I've seen for it is for testing. You actually see it all the time in testing, where you want to test some feature of your web application or something, but you don't want your test to actually change the actual database. Well, so then you could monkey patch out the calls to the database. Your database layer could monkey patch that out and run your test as if you were running on the database, but really it's just been monkey patched away. So there's very legitimate use cases of this. If you're curious about that, I would look up mock and patch, which are built-in things in Python. So anyway, I want to move on here because we've got a lot to do. So if you haven't finished your peer grade, that's okay. You have until midnight, so I would just go ahead and close your computer so that we can do some closures. All right, closures. So today we're going to go over some other stuff that isn't closures, and then we're going to get to closures. And the reason we're going over this is because it's really useful for this, but they're not directly related, so it's going to be kind of a two-parter. And I want to go through the first part kind of quickly. I'm going to not touch every single detail, because there's a lot of them, and honestly, if you find yourself needing to know the details here, I look it up, you should look it up, it's just not worth memorizing. But the ideas I want to go over because they're important. So, keyword arguments. Let's say we have a function here. It takes in 3 things and then it multiplies them, whatever. And we call that function, we get what we expect to be 80, because 10 times 2 to the power of 3 is 80. When we called this function, though, we didn't specify what these things were, so it's kind of hard to tell what actually, like if we didn't have the function definition right here, it would have been hard to tell what these 3 values actually represent. So that's a problem. And we'll fix that problem here. But first, when you define the function, you can actually define a default argument. Who's used the default argument in Python? Okay, a handful of people. So yeah, when you define a function, you can define a default along with it. And what that's going to do is it's going to make it so that when you call that function, you don't have to supply that argument. And if you don't supply it, it will use the default. So here, we didn't supply the exponent. Default is 1, so we got 10 times 2 to the power of 1, the default. Fun fact, if you specify a default here, it has to be immutable. Does anybody know why the default value of an argument has to be immutable? Any guesses? Mm-hmm.
Like different instances will point to the same data structure.
What do you mean, instances of what?
For example, you call math with a list, and you call it somewhere else with the same list, like with the same object.
You mean if this is a list here? Yeah. So it turns out Python does something a little unexpected with default values here. You might think that this default value is evaluated every time you call the function. So like every time we call math, it's going to say, oh, we need a default here. What was the default? Oh, it was 1. That's kind of what happens, but actually what Python does is it evaluates this default once when the function is defined, and then never again. And that means that there is exactly 1 value here for the function, and it's shared among all the function calls. So yeah, let's say like the default argument here was a list. If this is a list, then we could call this function and we wouldn't have to specify anything, we would use the default argument. And then let's say this function modified that list. Then the next time we call that function, the default won't actually be the list that we put here, it'll be the modified version. So that's just a quirk that is a result of how Python evaluates that default. So not hugely important, but it's kind of a fun fact. These should always be immutable. So just like how we can specify a default when we define a function, we can also use the exact same syntax when we're calling the function. But instead of specifying defaults, we're specifying exactly what values go with what parameters. So this is a different way of defining functions, defaults. This is a different way of calling functions with keyword arguments, explicit keyword arguments. And you can see here the cool thing about this is that we can change the order of the arguments. So, exponent was defined as the last argument, but when we use the keywords, we can put the arguments in whatever order. So that's convenient, one. And two, it's more explicit because up here it's kind of hard to tell exactly what these values were. If we specify the keywords, then it's very clear what those values were. Question?
What's the advantage of having it out of order?
Advantage of having them out of order.
Like being able to have
I wouldn't say there's an advantage to having the arguments out of order, but there is an advantage to being able to put them in any order. A lot of functions will take in parameters where the order is not inherent to the function at all. So like, a function might take in a bunch of options, like should we print a standard error or print a standard out? Should we buffer or should we not buffer? All of those options, there's no reason that the buffering option makes sense to come before the standard out versus standard error option. All those options are just kind of unordered options, so it doesn't really matter. But, there's no clear reason why there should be any order. So it's nice to be able to put them in any order. It prevents you from having to look up the order when you call a function. Yeah, great question. When we do this, we get what we expect. We get the 1 times 2 to the 2 is 4. Alright, how about this? What is this? Well, it looks a lot like our function definition up here with default arguments. But there's actually a problem here. We conveniently put the default argument at the end up here, which is nice because then when we did this, it's pretty unambiguous. We left out the third argument. So 10 is the coef, 2 is the base, and exponent was the missing argument here. But now that's not so clear. What if we called this function on just one argument? What is that one argument? Like, what if we called math on 5? 5 would be what? Base or coef? Unclear which one it would be. And so it turns out that Python does not allow this. Python forces you to put all of your default arguments at the end. So that's just, again, another quirk of Python and how it deals with these default arguments, keyword arguments. Questions about default keyword arguments? Alright, how many rows are there in this classroom? 1, 2, 3, 4. Let's get one question per row.
Is there a max number of arguments that you can specify?
That's a great question. No. There's no maximum number of arguments, unless the parser would refuse to parse it. But not that I know of. Not that I know of.
So if you put any arbitrary code as the right-hand value, default parameter,
Could you put anything in here?
yes, it's like an exec function of passing a link.
Yeah, so you can put anything here as the default argument, and it doesn't even have to be immutable. It can be mutable. It's just strongly discouraged because it gets very confusing. The one exception, you have to be careful about what scope you're in here. Like, I'm pretty sure whatever you put as the default argument, I don't think you can reference the other parameters. You can only reference things that are in the scope that the function is defining. Yeah, good question. I'm going to get the other rows first.
Where would those default args be stored, like on heap or stack? Or?
Just about everything in Python is stored on the heap. I'm pretty sure these would be stored on the heap. And I'm pretty sure they are, in fact, if they are, they're attributes on the function object. So this is part of the fact that functions are objects. If you refer to a function name dot dunder defaults, I'm pretty sure that'll be a dict of all of the defaults defined. And that's why it's the values here are per function, not per function call. Yeah. Let's see, I think we missed a row there. Should I laser point the row out? I don't want to blind anybody, but this row. Okay. Or did we missed 2 rows, kind of, didn't we? Yeah. Right.
If you have more than one default set, and like you have like 2 inputs required, can you call like only one of? Can you set like one of those like non-defaults that you're calling functions?
So you're saying like if we had maybe this was not a default, but this has a default and this has a default?
Yeah. You call like code and exponent equals 2, and just use the default for base.
Yep. Python does a pretty good job of figuring out what you meant to do here. You can do a pretty good combination of defaults and positional and keywords and non-keywords. There's just certain scenarios where it will complain if it can't figure it out. So it's kind of comforting. Like it'll usually be ambiguous and it won't compile, or it'll figure out what you meant. Yeah. Mm-hmm.
So where do you go with that? What if it's coef base equals 1, exponent equals 1, and then you say
Here or where? Here.
in the definition.
Base
Base is also optional.
Okay.
And then you call math of one number, exponent equals something, and then another number.
Good question. We'll get to that. Okay. All right. I don't know if we got every row, but I'm going to move on. Those are great questions, though. Thank you for humoring my way of asking for questions. I like to get questions. I don't trust myself to remember all the details that I meant to say, so I rely on you guys to ask me those questions so that I can remember that I meant to say those details. Okay, what about a variable number of arguments? In other programming languages, if you're familiar, there is usually a way of defining a function that takes in any number of arguments. Python's no exception. It has a way. And that way is star args. So if you define a function and you put a star before the formal parameter name, then that formal parameter will accept any number of arguments. So here we've got this multiply function that takes some star args, and then we multiply them all together and we return the result. And so now you can call mult on any number of arguments, and they'll all get packed into args, thus packing. So, what's going to happen here? Yep, this is going to output 1. Because out started at 1, loop through, there's nothing to loop through, return out. That kind of makes sense, kind of not. Multiplying nothing doesn't really make sense, to me at least. And so, how would we fix this problem if we wanted to force the user to put in at least one argument? Any ideas? Mm-hmm.
Do you like mult x on the args?
Yeah, exactly. All we have to do is supply one positional argument and then say star args. So now we can loop through, return to num. We can multiply everything just like we did before. This will be num. These will be star args. But if we try to supply nothing, we're going to get a missing positional argument error. So this is packing. Any questions about packing? Mm-hmm.
Question 4. So what we did in the previous slide was setting the default values. Could you also do that here where you don't know how many arguments it is?
Well, I think I got this question last time I taught this class, and I think I didn't know it then either.
I feel like you probably just have to define a variable and then set a default, but you wouldn't be able to just say with the star args and
Equals right up there. Yeah, I'm pretty sure you can't supply a default with the star parameter. Yeah, I'm pretty sure you can't. I've never seen it, so that probably means you can't. But I don't know. I mean, you can always just whip up a Python shell and try it out.
So the star arg should also have to go after the digital arguments, right? Because
Star args has to go after the default arguments.
No, the
Positional arguments.
positional ones. Because otherwise, if you have like star args 1, and you pass in like.
So that's one of the details that honestly I look up.
Okay.
Because in Python 3.5 and 3.6, yes, definitely star args has to come after all the positional args. But then I think in 3.7 that changed, so that's why I say I would probably look that up. I have a slide about that, so we'll move on. All right, keyword only argument. This was written when Python 3.6. Again, this might have changed very recently, but you can still do it. The syntax just might be slightly different. Let's say we switch the order of the parameters here. Before we had num and then star args. And then the exact same code, we return num. We multiply these things. Any guesses on what's going to happen? I mean, there's basically two options. It's going to work or it's not going to work.
I mean, missing a position every time.
Missing positional argument. Okay, we've got to look for missing positional argument. Any other votes?
I think it works.
Think it'll work?
Could work.
Could work? I like could work. That's true for just about anything. Missing keyword only arguments. So this is a new thing here. Turns out, and again, the syntax for this might have changed recently, like very recently, but at least for most versions of Python that are running these days, if you supply a positional argument after the star arg, then that argument needs to be specified with a keyword. And the reason is that this becomes a little bit ambiguous if you don't. Like, let's say we pass in, like here, we pass in 2, 3, 5, 10. Are 2, 3, 5, and 10 all supposed to go in args? Or does one of them go in num? Like, did the user forget a positional argument? Or did they not forget a positional argument? There's no way to know, really. And so, the way Python deals with this is any argument specified after the star arg has to be supplied with a keyword. That's why it's called a keyword only arg. Oh, darn it. I forgot that this was the next thing. I was going to lead into this, but what do you think this does? It's kind of an interesting syntactic manipulation of what we were doing before. If putting the star args here made everything that came after it a keyword-only argument, then what we're doing here is we're saying, similarly, there's a star. So everything after it should be a keyword-only argument. The only difference is that we don't care about the positional arguments. So the way I like to think of this is that we're using star args, but we just don't care about the args, and so throw them away. What this does is it makes it so that base and exponent are keyword-only args. So if you try to call this function, but just pass in the parameters by position, it's not going to work. We put in too many positional arguments. This function expects only keyword-only arguments. So the way you have to call this function is to specify the arguments. And so this gets back to what the question was about earlier, like why is this useful? Well, it's useful when we want to allow the user to be more explicit about what parameters they're passing in. In a lot of scenarios, there's going to be a ton of parameters here, and the order doesn't matter at all. If that's the case, we want to force the user to specify the keyword here because specifying the keyword actually makes the code a lot more readable. Like here, there's really no reason why base should come before exponent or vice versa. And so here we've forced the user to specify the exact parameter that we're putting.
If I have a function with like star args 1, comma star args 2.
Great question.
How do
You can't specify two star arguments.
Oh, you can.
not in the function definition. Yeah, great question. Other questions about this? Okay. So if we could pack positional arguments into one parameter called args, what about keyword arguments? What about when before, we were passing things in by keyword here, not by position. So when we do this, like, what if we want to accept any number of keyword arguments? Well, here we could accept any number of positional arguments by packing them into star args. To accept any number of keyword arguments, we pack them into star kwargs, which is just about the most fun thing to say ever. Star kwargs. And that is how you say it, star kwargs. So here's an example. This is definitely a contrived example. It's much harder to come up with examples for star kwargs. It's mostly used in framework code where you want to be able to deal with functions that take in whatever parameters they want. And to deal with that, you kind of need to be able to write functions that take in literally anything. This function takes in literally anything. There's nothing you can pass into this function where it'll say missing argument, blah, blah, blah. This function will take in anything. And that becomes a convenient thing later, and that's why I want to deal with it. If we print out what those things are, we get what we expect. The positional arguments are here in a tuple, and the keyword arguments are in the dictionary. What do we expect here?
Some sort of error.
Some sort of error, yeah.
The wrong order.
Yeah. So here, we pass in this keyword argument and then a positional argument, but now its position is kind of ambiguous, isn't it? Is it at position 0 or position 1? Unclear. And every time it's unclear, Python is going to throw an error. So it turns out this is an error. Positional argument follows keyword argument. So that goes to the question earlier, you cannot supply a positional argument after supplying a keyword argument. Okay, so similarly to packing arguments into a single variable in the function definition, you can unpack arguments into a function call. So this here is the method signature of print. And you can see actually print takes in any number of arguments. And this was what I was referencing on the Piazza note that I made last night. Is I had previously written homework where actually you had to kind of know about some of these things in order to do the homework, because print is actually able to take in any number of objects. And what it does is it prints out those objects separated by that, ending the line with that to this file. So what if we wanted to print every element in this array with one call to print? Well, what we would have to do is we'd have to access every element of that array and put it in print. That's the only way we could do it. We could loop through the array and call print on each thing, but with one call print, that's the only way. Except that we have unpacking. And so what we can do actually is we can star this array in the function call, and that will unpack the array into the positional arguments of the function. So this is kind of the inverse of what we were doing earlier. Before we were packing any number of arguments into a single variable. Here we're calling the function and unpacking a single variable into any number of arguments. And the same thing works for dictionaries, just like how you'd expect. You can star kwargs into a print function. So here we change the separator into a comma instead of just a space, and we're changing the end line to an exclamation point. So we get what we expect. Questions about unpacking? Mm-hmm.
What's the return value of star array?
Return value of star array?
Return type.
Of these calls to print?
But like just a star array.
What would a star array that is?
Is it like a two tuple?
I don't think that will compile. I think star, this kind of star syntax is specific to argument functions, or function arguments. So I don't think that would apply. Yeah, good question. Okay, I want to move on to the juicy part here. All right, to go over closures, we have to go over scope first. And I'm sure you guys probably already know what scope is. But I want to be very explicit about what scope is here, because it's going to become important. Python uses names to refer to things, and these names live in a dictionary. So here, we were in the global scope because we were just in the shell, and we referenced this name. Turns out that name was not in the dictionary, so we get a name error. So scope is two things, depending on how you use the word. If you reference the scope of a name, that's everywhere that name is defined. And if you talk about a scope in general, that's a block where any new names will remain defined. So that's scope. What is enclosing scope? It's the scope that contains a scope. So we'll see an example here. In this example, let's see, what's the enclosing scope of this if statement? Anybody? Foo? Yeah, this if statement has a scope, and its enclosing scope is foo. That's what you might think. But it actually turns out that in Python, if statements and for loops and while loops don't make a new scope. And you might have encountered this with weird bugs that you couldn't debug. It gets me every time. If you define a name inside of this if statement, it'll actually be defined outside of the if statement too, which is very different from C, C++, and Java. If statements don't create their own scope. They live in the scope that they were defined in. So actually, the enclosing scope of this if statement is actually the global scope, because its scope is the same as foo's scope, and so foo's enclosing scope is the global scope, because it was defined globally. So, trick question. What's the enclosing scope of bar? Foo, yep. What's the enclosing scope? What's the scope of param?
I hope it's food.
Well, we have to ask which param. How many params are there in this example? Yes, there are 2 params. What's the scope of this one? What's the scope of this one? Foo, yep. Less deceptive than it seems. Anything weird about this code here? Yeah, right? We're defining a function inside of an if statement. In just about every other language I know, that's not allowed, right? You have, let's say in Java, you have your class definition, and inside of your class definition goes function definitions. And the two shall never mix. Here, because Python is interpreted and is a scripting language, function definition is a script. It's just like any other statement in Python, which means it can go where any other statement in Python might go. So you can define a function inside of an if statement. We can define another function in here. Same goes for classes, actually. You could define a class in here. We could say else class foo equals, I already used foo, class, I don't know. So the point here is that you can define functions inside of functions, and that's going to become a little mind-blowing here in about 20 seconds. Oh, maybe more than 20 seconds. All right, first, free variables. So let's say we've got a main function here. We've got a count, and we've got an increment function that increments the count and returns it. And then we're going to print out the result of calling inc. And then we're going to print out the result again. All right, we're going to call main. What's going to happen here? Does anybody know?
So we upset.
If it's not upset, we would expect it to print 1 and then 2, right? But from my tone, you might be able to tell that it's going to be upset. It turns out this is a unbound local error count reference before assignment. I would get this error all the time, it's so annoying. And it only requires one line to fix. The problem is that in Python, this line here, this line here is assuming that count already exists, right? That line is basically the same as count equals count plus 1. But what was count before that? Well, you can't find it in that scope, right? We've made a new scope for ink here. And it can't find count in that scope. It's in the enclosing scope. And so we have to tell Python that. We have to say, Python, look in the enclosing scope. Count is a non-local. So we declare it as now non-local. And now, this will work. We get 1, and then we get 2. So that's kind of a nitpicky thing. What if we set count to 0 here? And then we print ink again. Bets on what's going to happen? It's either going to be 1 or 3, right? So who thinks it's going to be 1? Who thinks it's going to be 3? Alright. Turns out it is 1. The reason it might have been 3 here is that we've got this non-local variable. It's possible that declaring count as non-local actually made a copy of it or something. If we made a copy of count inside of this function here, then resetting it out here wouldn't do anything. Resetting out here would only reset this copy. This copy would remain at 2. And then when we call ink again, it would go up to 3. But it turns out it is the same variable. And in Python, you can even get a reference to that variable. Let's print out ink.undercode.cool 3 bars. Turns out that prints out count. So this, isn't very important code to be able to understand, but the point is that this count is recognized by Python as a special thing. It's a free variable. When we defined this ink function, count was actually referenced outside of it. And so it's a free variable. It can change independently of the function. So what if we had done this in the global scope? What if we have a count out here, and we define our ink, no main function here, we're just doing this in the global scope. We could declare non-local count, and we call ink. We actually get a syntax error. And that's because Python differentiates between non-local variables and global variables. So the way you would actually have to write this is you would have to say global count. So if your enclosing scope is the global scope, you just have to remember those variables are global. The reason it does this is that you might notice here this non-local thing, it threw a syntax error. That's actually really nice. That means that Python tried to determine what this count was at compile time. It turns out that these free variables and these, these non-locals, Python does a lot of work to optimize them so that they run quickly, and that involves making them not in a dictionary. So global variables, they're stored in a dictionary. Non-locals are actually stored in special places. So, alright. So you can see here the free variables are stored in a special place. We only get their name, and it's in a tuple. The globals are stored in a dictionary, and dictionary lookups are slower. So that's why Python does this optimization. Okay. I want to move on without questions because I have 5 minutes left, and I've finally gotten to the golden slide. Okay, so let's say we define x as 1. And then we define a function, make a closure. We set x to 2. And then we define another function, close. We print out x, so we're going to see what x is. And then we're going to return that function. So this is getting back to these first-class function things that we talked about last week. Functions are just objects, and by defining this function here, we've created a function object called close. It's a local variable. So we can return it, just like any local variable. So we're going to make a closure, we're going to call it C, and then we're going to call C. What are we going to get? Yeah, my arrow kind of gives it away. But it turns out we're going to get 2, which is a little weird. And it's weirder the more you think about it. 2 was defined in this scope, right? 2 was defined in make closure scope. And then we defined close, and it referenced the non-local 2. And then we returned it. This scope went away. Make closure has finished executing. That X has disappeared as far as we're concerned. Because this function here, it was defined in this function scope. This function is terminated. So this X is supposedly gone. But then we just call this, and we got 2. So it wasn't gone. You know, I would expect here, because we return close, and close looks up X, that it would look up X in whatever scope the function is in. But it turns out it actually looks up scope in whatever scope the function was defined in. So this function was defined in this scope, and so it's going to look up this scope for X. The problem is this scope has now returned, it's gone. So it turns out that Python actually saves information about your enclosing scope if it needs to, in order to make whatever functions that were defined inside of it work after that scope terminates. X is still 1. And we can see this here. If we print out C, free varies, we get X. That's because, just like in the last slide, X is a free variable here. It can change independent of this function. If we print out cell vars, we get nothing. C does not have any cell vars. If we print out make closure free varies, what do we expect?
X. Close.
Turns out it's none. Make closure doesn't have any free varies. It has a global variable, but we already saw global variables are handled differently. X is a global variable to make closure. That's defined somewhere else. Make closure does have a cell var. So the point here is that cell vars and free vars are kind of inverses of each other. To the closing function, it's a free variable. To the closure function, it's a cell variable. And it turns out that Python stores these things in things called cell objects. You can get them by referencing under closure on an object. Questions about this?
Is there a reason why we don't have to do non-local X in close?
Yeah, it's because before we were saying count plus equals. That's like saying count equals count plus. And it turns out Python evaluates the right-hand side of that equation first, the count plus. And it has to do with the order of operations. I can't remember exactly, but if you're just referring to a variable, you don't have to say non-local, but if you're adding to or changing that variable, then you do have to say non-local. Okay. So there's a bunch of really cool applications of this. I'm going to skip this one. Oh, this thing is so weird. Alright, one cool application of this is data hiding. So let's say we have an ink generator, and it returns an ink function that closes over some count, and then returns it after incrementing. It works just like how we expect. We get this ink function, and we call it a bunch of times, and we get values that increment. But the cool thing here is that the count variable is kind of inaccessible. The start was defined in the scope ink generator, which is now gone. So if we try to look up start, it's not there. So we were able to hide the count. That's kind of nice. Does this code look familiar to anybody from last lecture? I had this exact same code in the last lecture. These lines here. Turns out, closures and objects are very similar. Last lecture, we wrote something like this. We had a call method for ink class, and then calling the class created an instance, and that instance was callable. Do you guys see how that code is exactly the same as the code from last lecture? So it turns out that objects, just like how objects combine functionality and data in a single package, closures combine functionality and data. A closure is a function that closed over some data, and now the two are one. So closures and objects all kind of the same thing. Some are better for some applications, But it's important to know about both, and this will come back next week when we talk about decorators. So, hope your mind was blown.
Only a Python ninja can hide very well in plain sight.
I don't know. Attendance sheet? Did everybody sign
That's it.